In this module, we will dive into the interpreter pattern. It's not one you'd often use, yet it is pretty cool. It's used to define grammar and interpret languages. Let's learn what that's all about. I'm Kevin, and I'll guide you through this module. We will start by describing the pattern. As an example, we'll write a piece of code to translate Arabic numerals to Roman numerals. We will map that to a structural example and implement it in a demo. We'll continue with learning about use cases for this pattern and the pattern consequences. We will end the module by looking into related patterns. For the last time in this course, let's dive in. The interpreter pattern is a behavioral pattern from the Gang of Four library of design patterns. Its intent is to, given a language, define a representation for its grammar along with an interpreter that uses the representation to interpret sentences in the language. In other words, it defines a grammatical representation for a language and an interpreter to interpret the grammar. And that's also why it's not something you'll often create yourself. You don't define a language every day. Yet it is something we use a lot in our day-to-day programming life. When you use LINQ queries, behind the scenes an interpreter-like pattern can handle translation between LINQ and, for example, SQL. Or the interpreter for regular expressions, or even the way the C# compiler interprets the code we write. All of these could use a variation of this interpreter pattern. There are other patterns and possibilities. We will cover that once we get to the use cases. But know that it would be possible to use the interpreter pattern for all these examples. But what does that mean? Imagine the use case in which we want to translate Arabic numerals to Roman numerals. Say that we've got the number 181. How would we go about that? If we stick to the hundreds as a maximum, there's 999 possible outcomes, or 1000 if we include 0. Imagine the switch statement we'd have to write. That's completely unmanageable. Enter the interpreter pattern. We can look at 181 as a sentence in a grammar we're going to define. That grammar exists of a set of expressions. The first expression would be the 100 expression. The second one, the 10 expression. The third one, the 1 expression. Each expression is then responsible for translating the word, which is one number in our case, that's passed in. In other words, it's responsible for interpreting the word. So, we define a grammar through a set of expressions. You can call that a syntax tree. Each expression interprets a part of that syntax tree, which is a word. That means we don't need that huge switch statement anymore. What we do need is a way to define these expressions. Let's start with a Roman expression abstract class or interface that declares an interpret operation. This operation gets some information passed through, an object that contains info on what we want to translate and, typically, a way to store the result. Say we name that Roman context. And then we have 3 implementations of that expression. Roman 100 expression, which interprets the hundreds, Roman 10 expression and Roman 1 expression. Let's stick to 2 on our diagram to keep it more readable. It's up to the client then to define the grammar, the syntax tree, and provide Roman context. Before we implement this, let's map it to the pattern structure. We'll start with the first player, the abstract expression. This maps to our Roman expression abstract base class. What it does is declare an abstract interpret operation that is common to all nodes in the abstract syntax tree. Up next is the terminal expression. That's an implementation of the abstract expression. This implements an interpret operation associated with terminal symbols in the grammar. An instance is required for every terminal symbol in a sentence. So this maps to our Roman 10 and Roman 1 expressions. But what is a terminal symbol? And if there is something called a terminal expression, there's probably also something called a non-terminal expression, right? That is indeed the case, but we're going to park that for now as not to overcomplicate things. We will get back to terminal and non-terminal expressions after the demo. The next player is the context, which maps to our Roman context. It contains information that's global to the interpreter. Input and output properties are quite common on this. Lastly, we have the client. This builds or is given the abstract syntax tree, which represents a sentence in the language that the grammar defines. That tree is assembled from expressions. The client is also responsible for invoking the interpret operation. And with that, we know enough to implement our example in a demo. In this demo, we will create a translator which will translate Arabic numerals to Roman numerals. Let's start with the basics. We add a context class, Roman context, containing an input and output property. This is what will get passed through to our expressions. So for that we create an abstract expression base class. In our case, we name that Roman expression. I'm using an abstract class in this example, but as I've mentioned previously in the course when using abstract classes, you could also use an interface for this as long as you don't have the need to provide default implementation logic. Our Roman expression contains one abstract method, interpret, which accepts the context. Then it's on to the actual logic, the implementations of our abstract Roman expression class. In our example, these are the terminal expression classes from the pattern structure. Let's start simple with a 1 expression, so numbers 1 to 9. But how do we translate that to Roman numerals? Well, numbers 1 to 9 are represented as such in Roman numerals. So we could write a switch statement for all 9 possibilities. But if we think about it, we can simplify this. Take 3 for example. Translating that to Roman literals is 3 times capital I. That's the same as translating 1 to Roman literals 3 times. And 2, that's 2 times 1. So instead of having a switch statement for 3, 2 and 1, we could say that we write a statement for dealing with 1 and subtract 1 each time. That means that if we have the number 3, we will hit our logic to write 1 as capital I 3 times, resulting in I, which is what we need. With that in mind, we can simplify our logic to just 4 cases: 9, 5, 4 and 1. All the rest of these are combinations we can reach with simple subtraction. Putting code that translates to what you see on screen now. That takes care of our Roman 1 expression. The next one in line is the Roman 10 expression. And if we think about it, this follows likewise principles as the Roman 1 expression. These 9 different numbers don't necessarily result in a switch statement with 9 potential cases. They can be simplified to 4. So that results in a Roman 10 expression deriving from Roman expression, in which the interpret method takes care of these 4 potential cases. That leaves us with the Roman 100 expression, and you guessed it, we can implement likewise logic for this. And there we go. That takes care of our Roman 100 expression. That's it. On to our client to write a bit of code to test this. First, we create a syntax tree. We do need to import the interpreter namespace for that. So we create a new list of Roman expressions, stating we are going to start with the 100 expression, then the 10 expression, and then the 1 expression. That is the order in which our sentence will be translated, word by word. Then we create a context. When creating that context, we pass through the input, 5 in our case. We run through our tree of expressions and we interpret the input. After that, we write out the result. In this case, Roman 100 expression won't result in anything, and neither will Roman 10 expression, but Roman 1 expression will result in 5 being translated into 5 in Roman numerals. And let's do the same for a few other Arabic numbers. So we try to translate 81 and 733. Let me add a read key statement here. And let's give that a try. And there we go. My Latin is a little bit rusty, but I'm pretty sure these numbers are correctly translated. Up next is the part we previously skipped when looking into the pattern structure: terminal versus non-terminal expressions. When we looked into the pattern structure, we learned that one possible implementation of an abstract expression is a terminal expression. There's another possible implementation, a non-terminal expression. It's not applicable to our example, but it's nevertheless interesting to know about. So, all language consists of symbols. A symbol is the smallest meaningful part or unit of a language. For example, a word, a number, an operator, things like that. These symbols are called terminals, implemented through a terminal expression. When you think about it, you notice that all these terminals make up statements. For example, 5 plus 10 equals 15. That's a statement made up of a set of terminals. In a programming language, you could have a while or a conditional statement made up of terminals. Well, the statements that are made up of terminals and that are allowed by a language, those are called non-terminals. Non-terminals can consist of terminals and/or additional non-terminals. So that is what these two mean and how they differ. A non-terminal expression is symbolized by non-terminal expression in the pattern structure. It maintains a list of abstract expressions that make up the non-terminal expression. Interpreting a non-terminal expression is typically done via recursion on all the variables that represent it. And with that, we know about the difference between these two. Let's have a look at the pattern use cases.